Imagine standing at the base of a dune, maybe in the Namib Desert. It's huge, nearly 1,000 feet high. The air's shimmering, the sand just stretches out forever, kind of merging with the horizon. It almost ripples into nothingness. It's this image, right? Super iconic, almost alien. But what if I told you that this picture, well, it's partly true, but it hides a much deeper, way more complex geological story, one that might, completely flip your understanding of these landscapes. Welcome to the Deep Dive, your shortcut to being well informed. Today we're doing just that. We're diving deep into Earth's driest places, deserts, and the incredible, often surprising power of wind, and maybe counterintuitively, water in shaping them. We're going to try and uncover the underlying processes, challenge some of those common assumptions you might have, and show you how these forces literally sculpt our planet. And we'll do it all without a single visual, just relying on vivid descriptions and hopefully crystal clear explanations.
That's exactly right. Our mission today is to guide you through the intricate world of physical geology. We'll focus on how climate and geological forces really transform these extreme environments. Think of it like peeling back the layers,
Mm.
revealing the fundamental mechanisms at play, helping you visualize mountain ranges being born and then eroded, and understanding how everything from global air currents down to a single grain of sand plays a part.
Okay, so let's start with the basics, because I
Okay.
think even the word dry can be a bit misleading. When we say a place is dry, what are we actually talking about? Is it just about how much rain falls in a year? Because I have heard of places that get very little rain, but they don't really feel like a desert.
That's a perfect place to start, yeah. And you've hit on a really common misconception. A dry climate isn't defined just by the annual rainfall total. Climatologists actually define it as a situation where the yearly precipitation is less than the potential water loss through evaporation. So temperature becomes a huge factor here. For example, maybe 15 to 25 centimeters of rain. That could support forests, like coniferous forests in cold Siberia where evaporation is really minimal. But that exact same amount of rain falling in, say, Nevada or maybe Iran
Yeah.
would only support very sparse vegetation because the hot, dry air just causes so much more water to evaporate. It's all relative to the heat, you see.
Wow, okay, that's a huge clarification right there. So
Yeah.
it's not just the rain gauge we're looking at, it's the balance between rain coming down and how quickly that water just vanishes back into the air. And when you factor that in, the sheer scale of these environments must be enormous. How much of the planet are we actually talking about here?
Yeah, it's far more than most people realize. When you consider that balance, a surprising 30% of Earth's land surface is classified as dry.
Hmm.
That's a massive amount. It covers more land area than any other climate category, actually.
Mm.
And within these water-deficient regions, we often distinguish between two main types. There are deserts, which are truly arid, and then steppes, which are semi-arid. Steppes are essentially the more humid, sort of marginal variants of deserts. They act as transition zones.
Okay, so we know what dry means now and how much of the world it covers. 30%, that's huge. But the real puzzle is, why are these dry zones where they are? Is there a pattern? What's the sort of master architect behind their placement on the globe?
Well, that's where the grand design of global atmospheric circulation really comes into play. This is what creates these vast subtropical deserts. They're typically centered between, say, 20 and 30 degrees north and south latitude. Think of it like this. Heated air rises at the equator, right? Creating a low-pressure belt. This air then spreads out towards the poles, it cools, and eventually sinks back down around 30 degrees latitude. That's the subtropical high zone. Now, as this air descends, it gets compressed and warmed, and that process actually inhibits cloud formation. It stops clouds from forming easily. The result? You get clear skies, intense sunshine, and persistent dryness. This is exactly why you see a virtually unbroken desert environment stretching for thousands of kilometers from North Africa through the Sahara and the Arabian deserts all the way over to northwestern India. It's a huge belt. But that's not the only story. What's really fascinating here is how cold ocean currents can dramatically influence some deserts, specifically the west coast subtropical ones. Take the Atacama Desert in South America, right next to the cold Peru current, or the Namib Desert next to the cold Benguela current off Africa. These cold waters chill the lower atmosphere, and that prevents the upward movement of air that you need for clouds and precipitation. In fact, these deserts are often cool, sometimes even foggy, which directly contradicts that sort of hot, sunny desert stereotype we all have.
Wait, hold on. Foggy.
Yeah, foggy. The Atacama, for instance, it holds the unenviable title of the world's driest desert. Some areas there get mere millimeters of rainfall annually, or sometimes none. No recorded rainfall ever. and yet it can be foggy.
So you're telling me you can have a desert right next to the ocean, it's foggy, and it's one of the driest places on the entire planet. That just completely reshapes my mental image of a desert. I think, yeah, most people would find that hard to believe.
It absolutely challenges our preconceptions, doesn't it? And there are still other ways deserts form. Beyond the subtropics, we also find middle-latitude deserts. Now, these aren't controlled by those high-pressure belts we just talked about. Instead, they form deep in continental interiors. They're simply too far removed from any oceanic moisture source to receive significant rainfall. The Gobi Desert in Central Asia is a classic example. Moisture-laden air just can't make the journey that far inland. And this also brings up an important question. What role do mountains play in all this?
Yeah, I was wondering about mountains.
Well, the answer is profound. Mountains create what we call the rain shadow effect. When prevailing winds carry moist air, say from an ocean, and they hit a mountain barrier, they're forced to rise. As that air rises, it expands and cools, which leads to cloud formation and precipitation, but only on the windward side of the mountain, the side facing the wind. But then, as that now dry air descends on the other side, the leeward side, it warms up and gets compressed, and that makes cloud formation highly unlikely.
Ah, okay. So one side gets all the rain, the other gets dryness.
Exactly. You see this clearly in western Washington state. The Olympic and Cascade Mountains create a semi-arid rain shadow to their east. The Himalayas have a similar, even more dramatic effect, blocking monsoon moisture from reaching Central Asia. And this connection, this link to mountain-building events, which are caused by colliding tectonic plates, it really shows how geology itself profoundly influences climate patterns.
So, okay, you're basically saying our entire mental image of a desert, hot, sandy, endless sun is like largely a mirage itself. That's a huge claim. Let's tackle some of these common misconceptions head on, because I know I've definitely had a few. What are the biggest things we get wrong about deserts?
Okay, yeah, let's bust some myths. Here's the first huge mind shift for most people. The iconic sandy desert you picture. It's mostly, well, a myth in terms of coverage. Sand actually covers only a small percentage of most desert areas. For example, only about 10% of the Sahara is sand. Much of a desert is bare rock, gravel, or exposed bedrock.
Only 10%. Wow.
Yeah. Second, deserts aren't always hot. We mentioned the Gobi Desert. It can experience average high temperatures of minus 19 degrees Celsius in January. Even Phoenix, Arizona, a desert city, has an average January minimum just above freezing. And third, and this is probably the most important one, contrary to popular belief, running water, not wind, does the greatest amount of erosional work in deserts.
Whoa, okay, hold on. I need to unpack that last point again. If it's so dry, how on earth can water be the main sculptor of these landscapes? It seems completely counterintuitive.
It really does, doesn't it? But it's about the intensity of the water events, not how often they happen. Most desert stream beds are dry most of the time. They're what we call ephemeral streams, meaning short-lived. They only carry water in response to specific, often sporadic rainfall events. But when those rare heavy showers do come, they are often torrential downpours. And because the vegetation is so sparse, there's almost nothing to hinder the runoff. This leads to extremely rapid and powerful flash floods. These floods arrive suddenly, they carry enormous amounts of loose surface material, and then they subside quickly. The amount of erosional work done during a single short-lived event is truly impressive.
So these are the washes and arroyos you hear about.
Exactly.
Yeah.
The western U.S., you might hear them called a wash or an arroyo. In the Arabian Peninsula and North Africa, they're often called wadis. Different names, same powerful, ephemeral process. And this really is a crucial takeaway for you, our listener. Even though it's infrequent, running water is the most important erosional agent in deserts, not wind. Wind's main role, as we'll explore next, is really more about transporting and depositing sediment.
Okay, that's a major shift in perspective. So if water does most of the actual carving, what exactly does the wind do? What's its story in these vast, dry landscapes? Because, when I think of deserts, I immediately picture those towering sand dunes. So while water's carving is wind, then the great mover and builder shaping those iconic features.
Exactly, you've got it. Wind certainly has a crucial role, primarily in transport and erosion, but it operates quite differently from water. Because wind has a much lower density than water, it's less capable of picking up and carrying really coarse materials, like large pebbles or rocks. However, unlike water, which is confined to channels like streams and rivers, wind isn't confined. It can spread sediment over absolutely vast areas and even carry fine particles high up into the atmosphere.
Okay, so how does it move stuff? How does wind transport sediment?
Right, let's look at that. First, there's the bedload. This consists mainly of sand grains. These move primarily by a process called saltation. It comes from the Latin word saltere, which means to jump. When the wind gets strong enough, sand grains start to skip and bounce along the surface. A moving grain hits the ground, maybe dislodges another grain, which then bounces and hits another. It creates this chain reaction.
Like little billiard balls.
Kinda, yeah. What's fascinating is that this saltating sand seldom travels more than maybe half a meter to 1 meter above the surface, even in very strong winds. So it's like this rolling, low-altitude carpet of sand moving along. Then, distinct from that, there's the suspended load. This is made up of much finer particles, dust, silt, and clay. These tiny particles can be swept high into the atmosphere and remain airborne for hours or even days. Their flat shapes and the turbulence in the air easily counterbalance gravity. This dust is often first kicked up into the air by those bouncing sand grains, the saltation process, or other disturbances. Think of a car driving on a dry dirt road kicking up dust.
Right, you see that all the time.
And we've seen dramatic examples of this long-distance transport. Dust from the Dust Bowl in the U.S. during the 1930s actually reached New England. And plumes of Saharan dust, an estimated 40 million tons every year, regularly cross the Atlantic Ocean to reach South America.
40 million tons, traveling across an entire ocean. That really puts the wind's carrying power into perspective, even if it's just fine dust. Okay, so it moves stuff. How does wind actually erode the landscape itself?
Good question. Wind erosion takes a few distinct forms. One is deflation. This is simply the lifting and removal of loose material, sand, silt, dust by the wind. While it can be subtle to observe, because, an entire surface is being lowered gradually, it can be significant over time. During the 1930s Dust Bowl, as I mentioned, vast areas of farmland were lowered by as much as 1 meter in just a few years due to deflation. Deflation often creates shallow depressions called blowouts. Their depth is typically limited by the local water table. Once deflation reaches damp ground, the moisture helps hold the particles together, and sometimes vegetation can take hold, preventing further erosion downward.
Okay, so deflation lowers the ground. What else?
Another really interesting feature we often see is desert pavement. This is a surface layer that's closely packed with coarse pebbles and cobbles. It often looks like a mosaic, maybe just 1 or 2 stones thick with finer material underneath.
How does that form? It seems like the opposite of deflation, removing fine stuff.
Well, there are actually 2 main hypotheses, and they're kind of related. One is exactly what you said. Deflation removes all the finer sand and silt particles, leaving the coarser pebbles and cobbles behind, which gradually settle into a packed layer. The other hypothesis suggests that wind-blown dust actually accumulates on the surface and then sifts downward through the spaces between existing coarse particles. Over time, this accumulation of fine material underneath effectively lifts and concentrates the larger stones on the surface. It might be a combination of both processes.
Huh, interesting. Okay, what about abrasion, like sandblasting?
Exactly. The third process is abrasion. This is where wind-blown sand physically cuts and polishes exposed rock surfaces. It's nature's sandblaster. This creates features called vetifacts. These are stones that have been shaped, polished, and sometimes pitted or grooved by the constant impact of saltating sand. They often develop sharp edges and facets pointing into the prevailing wind. On a larger scale, abrasion helps form yardings. These are streamlined, often elongated, wind-sculpted landforms that are oriented parallel to the prevailing wind. They can be quite large. You find yardings in places like Peru's Ica Valley that are up to 100 meters high. But it's really crucial to clarify here. Abrasion's effect is limited vertically. Remember how saltating sand rarely travels more than about a meter high?
Right, the low-flying carpet.
Precisely. So abrasion primarily affects the base of rock formations. It doesn't carve out tall features like pinnacles or those balanced rocks you sometimes see pictures of. That kind of large-scale sculpting is usually the work of weathering and, again, running water finding weaknesses in the rock.
Okay, that makes sense. So wind moves sand and dust, lowers surfaces through deflation, creates desert pavement, and sandblasts rock bases. Now, when the wind finally slows down, it has to drop all that stuff it's carrying. And that's where we get some of the desert's most iconic and, frankly, really beautiful features, right? The dunes.
Indeed. This is where wind deposition comes in. You get dunes, which are essentially mounds or ridges of sand formed from the wind's bedload, that saltating sand.
Yeah.
They start to form whenever the wind encounters some kind of obstruction, maybe a rock outcrop or even just a clump of vegetation. This creates a wind shadow behind the obstruction where the air slows down. As the air slows, it loses energy and can't carry as much sand, so the sand starts to accumulate in this protected zone. As more sand collects, the mound grows and eventually becomes a dune, which itself then acts as a bigger obstruction.
And they have that characteristic shape, don't they?
They do. Dunes typically have an asymmetrical profile. There's a gentle windward slope, the side facing the wind, where sand moves up gradually by saltation. And then there's a much steeper leeward slope called the slip face. Sand accumulates at the crest, the top edge of the dune, and then periodically cascades down the slip face due to gravity. This slip face maintains a pretty consistent angle called the angle of repose, which is usually around 34 degrees for loose, dry sand.
So they actually move.
Oh, absolutely. This continuous process, sand moving up the windward side, accumulating at the crest, and sliding down the slip face, causes the entire dune to slowly migrate in the direction of the prevailing wind. Migration rates can vary, but sometimes it's as much as 15 meters per year. This is why you see active dunes encroaching on roads, fields, even buildings in some desert regions like in Egypt or Kuwait, where they sometimes need protective fences around oil installations.
And this process leaves a record in the rock.
It does. As sand is deposited on the sloping slip face, it forms layers that are inclined relative to the surrounding area. These sloping layers are called crossbeds. When dunes get buried by later sediments and eventually turn into sandstone, these crossbeds can be beautifully preserved. They're a telltale sign of ancient dune environments. You see prominent, large-scale crossbedding in the sandstone walls of places like Zion National Park in Utah. It's direct evidence of ancient deserts.
What's really fascinating, though, is the sheer variety of dune shapes. They aren't just random piles of sand. They seem to assume these surprisingly consistent and distinct patterns.
That's absolutely right. While there are many variations and complex forms, geologists classify several basic dune types. The specific type that forms depends on factors like the consistency of wind direction, wind velocity, the amount of sand available, and also the presence or absence of vegetation.
Okay, can you give us a quick rundown of the main types?
Sure. You have Barchan dunes. These are solitary crescent-shaped dunes with their tips or horns pointing downwind. They tend to form where sand supply is limited and the ground surface is relatively flat and hard. Then there are transverse dunes. These form where sand is much more plentiful and vegetation is sparse. They develop as long ridges oriented perpendicular or transverse to the prevailing wind direction. They often merge together to form vast sand seas, also called ergs.
Like the classic image of endless waves of sand.
Exactly. Related to those are barchanoid dunes, which are sort of intermediate, forming scalloped rows of sand that look like connected barchans. Then you have longitudinal dunes. These are long ridges of sand that form parallel to the prevailing wind direction. They're common where sand supply is moderate and the wind direction might vary, but stays within the same general quadrant. Some of these can be absolutely enormous, reaching heights of 100 meters and lengths of 100 kilometers or more in places like the Sahara or the Arabian Peninsula. There are also parabolic dunes. These are U-shaped, but unlike barchans, their tips point into the wind. They often form where vegetation partially covers the sand, anchoring the tips while the central part of the dune migrates downwind. You frequently find these along coastlines. And finally, star dunes. These are isolated hills of sand with complex, multi-pointed bases. They develop in areas where the wind direction is highly variable throughout the year.
Wow, that's quite a range. Barchan, transverse, longitudinal, parabolic, star. It really shows how wind acts like an artist, sculpting the sand based on the conditions. Now, beyond sand, you mentioned earlier that wind also deposits something else entirely different called loess. What exactly is that, and how is it different from dunes?
Right, loess. Loess refers to extensive blankets of wind-blown silt, so much finer particles than the sand that makes up dunes. Unlike sand dunes, which are typically shaped into distinct mounds and ridges, loess deposits tend to form widespread sheets or blankets that can cover large areas, often draping over existing topography. One characteristic feature of loess is that it often maintains nearly vertical cliffs when eroded, even though it's unconsolidated, and it generally lacks visible layers or bedding.
Where does all the silt come from?
There are two primary sources for major Longzhi deposits globally. First, directly from deserts. The thickest and most extensive Longzhi deposits on Earth are found in western and northern China. Here, enormous quantities of silt have been blown from the vast deserts of Central Asia for millennia. These deposits can be incredibly thick, sometimes over 100 meters, and it's this yellowish silt that gives the Yellow River, the Honghe, its distinctive color and name. The second major source, and perhaps less intuitively, is glacial outwash. During the ice ages, melting glaciers produced huge amounts of finely ground rock flour, or silt. Strong winds blowing across the barren floodplains in front of the retreating glaciers picked up this fine silt. This happened extensively in regions like the United States Midwest, Iowa, Illinois, Nebraska, and also the Pacific Northwest, as well as parts of Europe. This wind-blown glacial silt was then deposited as thick blankets, often accumulating on the eastern sides of major river valleys. And importantly, these loessy deposits have developed into some of the most fertile agricultural soils in the world. So there's a direct link between ancient ice ages, wind deposition, and modern farming productivity.
That's amazing. From glaciers to farmland via the wind. So let's try to wrap this up. What have we really discovered today about Earth's deserts and the powerful, sometimes subtle, hand of the wind? What are the big takeaways for our listeners?
Okay, let's recap. First, deserts are fundamentally defined by a water deficiency, where potential evaporation exceeds precipitation. It's not just about low rainfall amounts. Second, their global distribution is largely controlled by atmospheric circulation patterns, specifically those subtropical high-pressure zones, or by geographic features like mountain ranges creating rain shadows, or just being deep inside continents. Third, and this is maybe the biggest perception shift for many, water, even though it's infrequent, is the primary erosional force in most deserts, carving landscapes through powerful, short-lived flash floods. Fourth, wind, while not the main sculptor, is a highly effective agent of transport. It moves sand close to the ground through saltation and carries fine dust in suspension over vast distances, even across oceans. Wind erosion creates specific features like deflation hollows, blowouts, desert pavement, ventifacts, and yardings. And finally, wind deposition creates those iconic desert landscapes. The diverse and often beautiful dune fields, barkens, transverse, longitudinal, parabolic, star dunes formed from sand, as well as the widespread, often very fertile, blankets of loess derived from silt.
It's truly incredible when you put it all together, thinking about how these often misunderstood environments are constantly being shaped by forces, both incredibly powerful, like flash floods, and really subtle, like the slow drift of dust across continents. It reveals these deep connections between climate, geology, and even, as you said, human society and agriculture through soils. It really highlights how dynamic our planet is, even in places that might seem utterly still or unchanging. Okay, so here's a final provocative thought for you to take away. Considering the profound impact of even infrequent water in deserts and the significant role of wind in moving vast quantities of sediment, what might future climate shifts, whether that means increasing or decreasing precipitation or maybe changes in global wind patterns, what might that mean for these vast dry lands and for the sometimes large populations that actually rely on them? Definitely something to mull over until our next deep dive.